Welcome to another warm-up, this one focusing on optimization. So you have a 4-foot by 8-foot piece of cardboard that you want to fold into an open box by cutting the corners and folding up, as I drew in the picture. How would you make your cut to get the most volume out? So take a few minutes, pause the video, give it a try. Alright, that's about all the time I'm going to give you. Hopefully you paused that video. Let's go ahead and make sure that we are clear on this picture. And one of the ways we can do that is by labeling this. So I'm going to go ahead and label the length of this cut that I need. So really what I need is this X. And the question is asking me, what should that X be? If you didn't get that far, well, maybe pause the video again and give it another try. The idea then is that I'm going to take this square out, and this square out, and this square out, and this square out. They're all going to be X by X squares. And then we're going to fold up along these dotted lines to create an open box that has no top. Okay, so if I really wanted to, I could label each and every one of these X's. The other thing that's important here is that this is a 4 and this is an 8, which means that I actually know how long those dotted lines are as well. So this is going to be 8 minus 2x, and this is going to be 4 minus 2x. Okay, that was a lot of pre-work. As always, maybe you took a little bit of a different approach, and you started off where we normally start off, which is what on earth are we optimizing? So in this case, we are optimizing volume. We want to get as much volume as possible. And so volume, maybe you started off with something like, well, it's a box, so base times height times width, or length times width times depth. All of them are fine, but really in this context, we want x's. So the height of this box, well, here, let's just do length times width times height, just to get you started. But really for us, this is, well, it's going to be, that base will be 4 minus 2x times 8 minus 2x. That's the area of that rectangle, this base right here, times the height. Well, what's that height going to be? That's just going to be x. Okay, so hopefully you got that far. If you didn't, again, well, each time I push you a little further, maybe stop and see, can I get the next part? Being honest with yourself about what part is causing you trouble is going to save you so much time in getting better and in getting help. Okay, now often we would look for a constraint, but we actually don't need one this time. Why don't we need one? Well, volume is really a function of one variable, and so we'll use our constraints to lower it to one variable. That's kind of a practical answer. The better answer is just that there isn't one. The constraints are sort of naturally included here in the fact that this is 8 by 4. So there is a secret constraint happening. We could write it if we want to, but it's not going to really change anything else, which is just that x has to be, well, between 0 and what's the biggest x could be? 2. So there is that constraint, but that's not going to really change our volume equation for the optimization purposes. Great. Now this is really a calculus question. Can we find the maximum of what looks like to be a cubic polynomial? Let's go ahead and take a derivative of this thing. So find the max. The first thing I want to do actually is not to find that max. I just want to multiply this out to make our lives a little better. So I think if I can do this right, foiling that first thing out, just leave this x out front. I get 4x squared, and then I get a minus 8x and a minus 16x, and I get a plus 32. Neat. I can go a little further. From there, looks like I can pull out a 4, and I can bring together what's left of the inside, so that'd be a 2 and an 8, so this would be minus 10x plus 8. In fact, I did that wrong, didn't I? When I combine that 8 and that 16, I get 24, and then I pull out a 4, and I get 6. Whew, that was close. Okay. I can even go a step further. I could do the product rule on this if I wanted to find that derivative, but why? Right? Why not just go ahead and multiply this out one more time and get x cubed minus 6x squared plus 8x. Maybe you pulled out that 4, maybe you didn't. It's not going to have a big effect on your derivative. It'll make our next step a little easier. So let's find dv dx. That 4 stays out front. The 3 comes down. The 2 comes down. This becomes an x plus 8. I want to set that equal to 0. So when I set equal to 0, I can go ahead and divide by that 4 also. Again, now that we've seen a couple of these, I often skip a little algebra step in the middle. So 3x squared minus 12x plus 8. Okay, so I set it equal to 0. I divided by that 4. Now I need to find where this quadratic is equal to 0. Do you think you can do it? Let's give it a try. Luckily, there's a nice formula for things like this. I don't think I can factor this in my head super easily, so I'm going to use that quadratic formula. When that quadratic is equal to 0, I get x equals negative b, so plus 12, plus or minus the square root of b squared minus 4ac all over 2a. Great. A little bit more cleaning up here. So I get 12 plus or minus the square root. 144 minus 96 is 48. All over 6. Great. Now, I can go ahead and make my life a little easier. Well, let's wait till the end, actually. We know that x is going to need to be between 0 and 2. So one of this plus and minus here, one of them is going to be in that domain and one is not. And if that's not clear to you which one, well, then it should be clear in just a minute. In fact, let me go ahead and clean this up a bit more. 12 over 6 is 2 plus or minus the square root of 48 over 6. In fact, I can pull out a 16 as a 4. 48 divided by 16 is 3 over 6. So again, I pulled out a 16 because 16 times 3 is 48. That 16 comes out of the square root as a 4. What is left is I get 2 plus or minus 2/3 the square root of 3. That's about as far as I think I want to simplify that. So one of these is going to be bigger than 2, and one of them is going to be smaller than 2. So I think the one I'm definitely going to want is 2 minus 2/3 square root of 3. Check. If you're not sure, that should be greater than 0 and less than 2. That is the x value that I want to optimize this cut. You should also, by the way, check that that what you get out is in fact a maximum and not secretly a minimum. One way to be sure of this is that the volume is going to be 0. The volume should be 0 at 0 and 2, and positive everywhere in between. And so because this thing looks like a polynomial, then this must be a maximum in between 0 and 2. It's our only critical number in between 0 and 2. So sometimes, we've seen this several times, we can get away without doing that first derivative test or that second derivative test. But if you want to be really sure, feel free to do a first or a second derivative test on our function. Great, that was our warm-up. This one didn't really need too much of a constraint, but this is a classic example. You see it in almost every textbook somewhere.